All right, class, welcome to Chapter 3, Compounds, How Elements Combine. So in the last chapter, Chapter 2, we discussed the nucleus of an atom, and in Chapter 3, we're going to be discussing the the electrons outside of the nucleus in an atom, and how those electrons are arranged, and how that produces all the different chemical reactions that we see in the world around us, aside from nuclear chemistry, which we just discussed in Chapter 2. So first we're going to discuss how electrons are arranged outside of the nucleus, in that area surrounding the nucleus. And we're going to discuss something called the octet rule. So some atoms on the periodic table are going to attempt to reach a full octet, or they're going to want to have 8 electrons in their outer shell. And we'll talk about what those shells are in a second. In trying to do that, some atoms will form ions, and other atoms might form covalent bonds. So we'll talk about those two different types of bonding, ionic bonds and covalent bonds. The next thing we'll discuss is the mole and molar equivalence. This is how we count atoms and compounds in the field of chemistry, because they all have different weights. So it's not easy to count them by grams. Like an atom of hydrogen weighs a different amount than an atom of carbon. So we use something called the mole, so that we can work in ratios of the different types of atoms. And the next thing we'll talk about is how do we predict the shape of molecules. So in section 3.6, we'll talk about getting covalent compounds into shape. We'll look at Lewis structures and be able to predict what's the shape of these things, and that'll help us when we move on to biological molecules. So if we can picture the shape of smaller molecules, then we'll be able to picture the shape of larger biological molecules such as protein and DNA and things along those lines. And then finally, we're going to talk about electronegativity and molecular polarity. Electronegativity and molecular polarity play a huge role in how molecules interact with other molecules around them. So some molecules might have an electrical pole, like our Earth has a north pole or a south pole, or like magnets have a north pole or a south pole, or a plus end or a minus end to a battery, and these things will attract one another. So things that are very polar might be very attracted to one another, and things that are very nonpolar might be very not so much attracted to other polar things. So it can it's how oil and water don't mix. Polarity describes the reason why that happens. So we already discussed in chapter 2 that electrons are attracted by protons. The electrons are negatively charged, the protons are positively charged. What we didn't discuss was electrons are these tiny things that move very fast, and they kind of orbit the nucleus like the Earth orbits the sun in a way, just on a much smaller scale. So these guys are zipping around, and for example here we have hydrogen and helium. So the hydrogen nucleus has a single proton, and so it can attract a single electron. The helium nucleus has 2 protons, and so it can attract 2 electrons. And these electrons are going to orbit around in this energy level, and this energy level we're going to call a shell. Now remember, electrons are negatively charged, so the electrons are actually going to repulse each other. So you can only fit so many electrons into each shell. Now, so for example, if we look at the periodic table of the elements, if you have your books out as well, you can take a look at the periodic table of the elements, and if you look at the first row of the periodic table of the elements, there are only 2 elements in that row. And the first reason is that the first shell, each row actually represents a shell of electrons outside of that atom. It's one of these energy levels. So the first row of the periodic table of the elements only has hydrogen and helium, because the first shell of electrons that we can have can only hold up to 2 electrons. After that, if we move down to lithium, which is the third element on the periodic table of the elements, lithium has 3 protons and can attract 3 electrons, but those 3 electrons can't all fit in that first shell. That first shell only holds 2 electrons, so our next electron has to fill into the next highest energy level. Electrons are always going to try to fill in the lowest energy level possible first. That means that they're going to try to get as close to the nucleus as they can. This makes sense. They're negatively charged. They're attracted to those positively charged protons. So we're going to fill in the shells that are closest to the nucleus first, and then we're going to continue to fill out the next shell, and then we're going to continue to fill out the next shell after that. As we get further and further away from the nucleus, the electrons in these outermost shells actually increase in energy. That's because they're further and further away from the nucleus, so their negative charge isn't quite as neutralized by the protons in the nucleus. So that upsets the balance of things. And there's a video that we'll watch in class that you can look up on YouTube. If you just look up alkali metals reacting with water, you can see that as we go from top to bottom on the periodic table of the elements, we're having an electron stripped out of the outermost shell. And at the bottom of the periodic table of the elements, that electron that's getting stripped out of the outermost shell of these alkali metals is in the upper steps here. It's at a high energy level. So as you go from top to bottom, the amount of energy in the reaction increases. So we understand now that these electrons are arranged in these shells, and the shells have different energy levels, and you can think of them as steps. It's not a smooth transition from one energy level to another. An electron's either at this energy level or the next energy level up. It's not a smooth transition, it's a full step up. So this is just another graphic representation of this. So if you look at the first column of the periodic table of the elements and go from top to bottom, we start with hydrogen. So hydrogen has one proton and attracts a single electron. If you go down, we have lithium. Lithium has 3 protons, and so he can attract 3 electrons. It takes 2 electrons to fill in his first shell, and so the third electron has to go to the next one. Sodium has 11 protons, and so he can attract 11 electrons. 2 can fit in that first shell. The second shell can hold up to 8, and the next one then therefore has to go in the next shell up. So if you notice, as we go in column 1, all of the elements of column 1 have something in common. They all have a single electron in their outermost shell. And that's because the periodic table of the elements is arranged to describe how electrons are arranged in the outermost shell of an atom's electron cloud. So just to review a few points, electrons exist at distinct energy levels, these steps on that staircase that we showed. They don't exist in between that. Electrons are generally going to try to occupy the lowest energy step first. That's because that's the ring or the shell that is closest to the nucleus. The electrons are attracted to the protons in the nucleus, so they're going to try to occupy that lowest energy step. And as these electrons get further and further away from the nucleus, their energy level increases. The energy level doesn't go up evenly as we go from one step to another. If you notice, the first step was like a really big jump, and it kind of tapers off after that. And that's because these shells, the surface area of the shell gets so much bigger that the shells can be a little closer to one another as you get further and further out away from the nucleus. So each one of these shells can hold a different number of electrons. For all intents and purposes for this class, we're really going to pay attention to something called the octet rule. So what's really important is that the first shell we know can only hold 2 electrons. So the number of electrons that can be held can be calculated by this formula 2 times n squared, where n is the number of the energy level. So in the first energy level 1, 1 squared equals 1, 2 times 1 is 2. So you can hold 2 electrons in the first energy level. In the second energy level, 2 squared equals 4, 2 times 4 is 8, so you can hold 8 electrons. In the third energy level, you can hold 18. For all intents and purposes in this class, we're going to ignore anything above 8 electrons. We're going to be talking about the octet rule. We're going to talk about some different atoms like phosphorus and sulfur. They have this third energy level. And so they can do weird things when they go to make bonds. But we're going to focus on this octet rule because this octet rule really does a great job of describing how hydrogen, carbon, nitrogen, oxygen, the halogens, most of the alkali metals and alkali earth metals, how they behave. So the octet rule is going to describe a lot of the atoms that are involved in biological chemistry. Some of the other atoms are going to break some rules, and so we're going to talk about exceptions to the octet rule. So what I want you to take away from this slide is an understanding that our first shell of electrons can hold 2 electrons. Our second shell can hold 8. Our third shell can hold 18, but for all intents and purposes, we're going to focus on 8 of those 18 electrons. in that outer shell. And we're going to keep in the back of our mind when we're talking about things like sulfur and phosphorus are in that third row of the periodic table of the elements, that they can break some of that octet rule because they have this larger shell. A really important definition for this chapter is the valence shell. So the highest energy level that contains electrons is the valence shell. The electrons in it are called the valence electrons. So if we think back on that image I had, or that slide I had, where we went hydrogen, lithium, sodium, potassium, all of those guys in their outermost shell of electrons had one electron. So the outermost shell for each one of those guys is called the valence shell. So for hydrogen, his first shell was his valence shell. For lithium, his second shell was his valence shell. For sodium, his third shell, and so on for potassium, his fourth shell. In each one of them, they had a single valence electron. These are the electrons that are involved in chemistry. So the electrons in that valence shell are going to be very close to the other atoms. If you think about our universe as a model for an atom, or like our solar system, if you have the sun in the center and you picture the sun as the nucleus, and you picture each of the planets and their orbits as one of these electron shells, you can imagine that on the atomic scale, these electron shells are pretty far apart from one another. So it's only the valence shell that can be involved in chemistry, most of the chemical reactions that we're going to study in chemistry. Not to say that you can't take an electron from one of those inner shells given enough energy. It can be done, but it's a lot harder. So we're going to focus on these valence shells. That's where most of the chemistry is going to occur. So the column on the periodic table, or the group, is going to indicate the number of electrons in the outermost shell. So if we look at group 1, which is hydrogen, lithium, sodium, potassium, all those guys have one electron in their outermost shell. If you look at this next one, which is like beryllium, calcium, magnesium, all of those guys have 2 electrons in their outermost shell. And as we skip the transition metal elements, we're going to go over to where boron is. We have 3, and then carbon has 4, nitrogen has 5, oxygen has 6, fluorine has 7, and then finally we come to the noble gases, and those guys have 8 electrons in their valence shell. When you have 8 electrons in your valence shell, it's a very stable atom. So that's where we're going to move into the octet rule. The periods, or rows, in the periodic table indicate to you which energy shell is the valence shell. So if you're in row 1 on the periodic table, your valence shell is the first shell. If you're in row 2 of the periodic table, your valence shell is the second shell, and so on and so forth. So here's just a graphical representation of what we were just discussing. So hydrogen has a single proton, and so you can attract 1 electron. Helium has 2 protons, so he can attract 2 electrons, and now he's got a full first shell. We move on to lithium. He brings another electron. That electron has to go to that next shell. We move on to beryllium on the periodic table of the elements. He brings another electron. That can stay in that second shell. We're still in that second row of the periodic table of the elements. Then we get boron, carbon, nitrogen, oxygen, fluorine, and neon. Now we're at a full shell. And once we go back down to sodium, now we are in row 3 of the periodic table of the elements. And so we have to have that extra shell now, and that's going to hold that first new valence electron in that extra shell. So just a quick review, we're just looking at a small portion of the periodic table of the elements, and I want to point out that the number of valence electrons in an atom is the same as the group number for these main group elements. So those 1A, 2A, 3A, 4A, all you have to do is look at what column or group is the atom in to figure out the number of valence electrons in that atom. So if I ask you about the halogens, which are in group 7A, and ask how many valence electrons are in these guys, you say 7. It's that easy. It's just the group number. So far, when we've talked about the number of protons and electrons in an atom, we've talked about atoms in their elemental states. So the elemental state of something has an equal number of protons and electrons. But things can react in such a way as to form compounds. One of the ways they can do this is to form ions. So when ions form, an atom either gains or loses an electron. And it does this in order to gain either a full or empty valence shell. Atoms are more stable if they have a full or empty valence shell. And there are several ways that they can obtain this. One way is to totally give up electrons or to take an electron. Another way is to share electrons in what we call a covalent bond. We'll talk about that in a little bit here. So we have two different types of ions that we can form. So ions that form when atoms gain electrons become negatively charged, and we call those anions. So fluorine is a great example of an element that forms an anion when it reacts to form an ion. So fluorine has 9 protons, with 7 of them in its valence shell. It's trying to get that valence shell of 8 electrons in its outer valence shell. So fluorine is a particular element that can steal an electron from someone else. For example, hydrogen here. Hydrogen is going to be our electron donor. So fluorine will steal that electron in this process as we move from left to right in this reaction sequence. And in doing so, it takes on a negative charge. Notice we went from fluorine to what we call fluoride, or F minus. So this new ion, or anion, is going to have an extra electron. So he used to have 9 protons and 9 electrons. Now he has 9 protons and 10 electrons. So the charge is 9 plus minus 10. So 9 plus for the 9 protons, and then negative 10 because the electrons are negatively charged. So fluorine now has a negative charge of negative 1. Our hydrogen, on the other hand, is turned into a cation. He's had an electron removed from him. If you subtract a negative, that gives you a positive charge. So we have a double negative there. That gives you a positive. So we can use another example, sodium. Sodium's on the opposite end of the periodic table of the elements from fluorine. So sodium's in group 1 of the periodic table of the elements, and he has a single electron in his outer valence shell. Now it'd be very difficult for him to totally fill that shell. He would have to gain 7 new electrons. That would just be taking on an enormous amount of charge. He doesn't have nearly enough protons in his nucleus to attract 7 additional electrons. So rather than trying to take on 7 new electrons, he's just going to ditch that one and totally get rid of that shell, and that will make him quite stable. So in doing so, he is going to become sodium with a positive charge. So he's lost that electron. Someone else, like fluorine, might have come along and taken that electron away from him and satisfied their octet rule. So someone else always gets the electron. It doesn't just float off into nowhere, and it forms a new ion. So these ions are called cations. So how do you remember anion and cation? Think about the anode and cathode of a battery. So if you think of your car battery, the cations are attracted to the cathode, and the anions are attracted to the anode. And that's where we get the plus and minus on the car battery as well. I want to point out another definition, which is isoelectronic, or it's isoelectric with something. So if you take a look now at the sodium ion now has the same arrangement of electrons as neon. So things can be isoelectronic with their nearest noble gas. That is, the noble gas that has the closest number of electrons to the new ion. So they have the same arrangement. So what this is telling us is that sodium ion is about as stable as neon now. It's a very stable little guy. He's going to behave differently from neon because he has a charge, but his electronically on the outside, his electron arrangement is very similar to neon's. So just as we could predict the number of valence electrons that an atom has based on where it's at in the periodic table of the elements, we can also predict the charge that an ion will take based on where it's at in the periodic table of the elements. with some exceptions. So if you look at the middle of the periodic table of the elements, we have the transition metals. The transition metals are called the transition metals because most of them can transition to have multiple charge states. So for example, iron can have a 2+ or a 3+ charge. Copper can have a 1+ or a 2+ charge. Some of them can't, however. You have zinc that just has a 2+ charge, or they can all be, of course, be neutrally charged in their elemental state. Some of them have a bigger gap between their charges, like lead has a 2+ and a 4+ charge. So those guys are a little bit difficult to predict charges. I'm not going to make you memorize those charges. You don't have to memorize anything about the transition metal elements here. Just know that they can have multiple charges. The guys that are not in the transition metal elements, so our alkali metals, our alkaline earth metals, and our nonmetals, those guys will be able to predict what charge they're going to have based on where they're at in the periodic table of the elements. So think about it. All the guys in group 1 have a single electron in their valence shell. In order to get a full valence shell, they will lose that single electron, all of them taking on a +1 charge in the process of that. Everyone in group 2 has 2 electrons in their valence shell. So they're going to have to lose 2 electrons. Minus -2 gives you a +2 charge. So calcium, for example, if it wanted to become an ion, would have to give up 2 electrons in order to do so. It would need 2 guys like fluorine or chlorine to come along to do that. So we can also determine what the molecular formula of ionic compounds is going to be based on where the constituents of the ionic compound are at in the periodic table of the elements. So for example, if we had sodium chloride, sodium has to give up 1 electron. Chlorine can accept 1 electron. So the ratio of sodium to chloride will be 1 to 1. Whereas if we have calcium chloride, calcium has to give up 2 electrons. Each chlorine can only take on 1. So you'll have the formula CaCl2. It will take 2 chlorine atoms to accept the 2 electrons from calcium to form the full ionic compound and make everybody happy. So just a quick review of what we've gone over in chapter 3.1 here. Elements in group 8A are our noble gases, are unreactive, they're inert. So they don't react under all but extreme conditions. And this is because they have that full valence shell of electrons. Most atoms are going to react in such a way to obtain that full outer shell of 8 electrons in their valence shell. This is what we call the octet rule. In order to do this, some atoms are going to give away electrons, others might accept electrons, and we're going to learn in just a second that even others can share electrons. So there are various different ways to achieve that valence octet, and that's what allows our world to form all of these different kinds of compounds that make up the world around us. A few things that we can do to predict the charge on main group ions. So if we take a look at the periodic table of the elements again, if you're on the left of the periodic table of the elements, you're going to be taking on a positive charge. So our metals are all going to take on a positive charge to form cations. Our nonmetals are on the right side of the periodic table of the elements. They almost have a full shell. So they're going to be accepting electrons and becoming anions. So they're going to take on a negative charge. Some of the transition metals are more difficult to predict, so they can form more than one charge. So that's something that we have to just understand, that we have to study those particular elements and memorize the different charges that they can take. You don't have to do that for the purpose of this class and this test. Another group that we're going to discuss are polyatomic ions. So there are many polyatomic ions. These are molecules that gain or lose perhaps protons or pick up an electron, and in this fashion they can pick up a charge as well. So we'll show some examples of polyatomic ions, and we'll discuss these later in class. Some of the most important polyatomic ions to understand, and we're going to take a look at these guys as structures and structural formula for examples in class. But there are different forms. The acidic and basic form of water. So hydroxide is the basic form of water. So this is found in antacids. Hydronium is the acidic form of water. So H3O plus. And nitrogen can form different polyatomic ions. There are many that are very common in biological systems. So ammonia is commonly found in urine. Nitrate and nitrite are nitrogenous nutrients that are very important for plant growth and bacterial life. And we use some of these as signaling molecules in our body as well. Chlorate and chlorite, these guys can be used as disinfectants, so they're biologically important. You don't have to memorize these guys' formulas, but I want you to, if you see them, I want you to recognize them as a polyatomic ion. It's got a charge, and it's got more than one atom involved. So it's a polyatomic ion, and that's the big takeaway here. So some of the other really important biological ones, carbonate and bicarbonate are responsible for pH buffers in our blood. Cyanide is a deadly poison, and we use it a lot in industry. So there's a lot of cyanide out, especially in the metal plating industry, in metal finishings. Acetate is a form of, it's the basic form of acetic acid. It's involved in many different metabolic processes. So lactate, sulfates and sulfites, those are often found in wines. They're a constituent of wine. Phosphate is an essential nutrient for life. It's responsible for the formation of the DNA backbone. It's essential for the formation of the DNA backbone, which is a ribophosphate chain. And so phosphate comes in many different forms. You can have phosphate, hydrogen phosphate, dihydrogen phosphate, and phosphoric acid is not ionic, so it's not on this particular table. Again, you don't have to memorize the names of all of these guys for the purposes of this class, but this is a group of molecules that you might want to start looking over this table and just familiarize yourselves with them, because we're going to see them pop up pretty often in class. These will pop up in a lot of biological any biological chemistry class that you take. They're important molecules, these polyatomic ions. So naming ions is really pretty easy. So when we name ions and ionic compounds, when we name an ionic compound, we usually start with the metal. We put the metal first. So we go kind of work our way from left to right on the periodic table of the elements. So for example, if you had sodium chloride, it's got sodium ion in it. So if we say sodium, typically when we just say sodium, we're talking about elemental sodium. That's sodium with a neutral charge. But if I tell you sodium ion, now you should be able to tell me, oh, what's the charge of that? It's got a +1. He said ion. So if I say, what's the charge of sodium? Sodium has a charge of 0. Because when I say sodium, I'm talking about the elemental state. Now if I say sodium ion, I'm talking about sodium with a +1 charge on it. Our transition metals, like I said, they can have multiple charges. So we can't just say iron ion, because iron could be iron 2 or it could be iron 3 ion. So we have to specify, and we do that with Roman numerals. So if it's iron 2 plus, we'd say iron 2 ion. If it was iron 3 plus, we'd say iron 3 ion. So same thing with lead. If we had lead 2 plus, it'd be lead 2 ion. If you had lead 4 plus, it'd be lead 4 ion with the Roman numerals in parentheses. For the nonmetal component, we stick this suffix IDE to replace the last few letters of the name. So if you had fluorine, would become fluoride. Chlorine would become chloride. Oxygen becomes oxide. You can have like metal oxides and things along those lines. For our polyatomic ions, the names vary quite a bit. You'll often see the suffix ATE or ate or ITE, ite, but it varies so much that it's just easier to try to memorize them as you come across them, in all honesty, for the polyatomics. So here are just some examples of biologically important ions. We've already discussed some of these. Sodium regulates fluid outside of our cells, found in our table salt, often in seafoods, an essential ion in the human body. Potassium is used to maintain ion concentrations in cells. So there's a lot of pumps that can be used to like move ions from one side of the cell membrane to another, and potassium is going to be very essential in maintaining those ion concentrations from one side of the membrane to the other. Calcium is not only important for building our bones, but it's found outside of the cell. The cell will pump it outside, and it'll pump it into these little vesicles inside the cell, the endoplasmic reticulum, and it'll store calcium, and then it'll release it to trigger different signals. Like it might be released in order to trigger the cell to say, if I'm a white blood cell, okay, now we need to trigger an immune response. Or if I'm a muscle, if the calcium is released, that might trigger, okay, we need to flex now. We need to flex that muscle, we need to contract. So calcium is used as a signaling molecule. Magnesium, important for nerve impulses. Iron, important for oxygen transport and oxygen metabolism. Our important anions, chlorine, found in gastric juice and outside of our cells, is again involved with fluid balance. Bicarbonate, HCO3, that is a buffer in our bloodstream. It's a very important buffer. It's actually made from CO2. CO2 can react with water and become H2CO3, which is carbonic acid. One of the H's floats off and it becomes bicarbonate. So that's a buffer, a pH buffer in our blood. It can buffer acids and bases to keep the pH of our blood roughly at that 7.2 to 7.4 range that we need our blood to be at to be healthy. Phosphoric acid, that controls the acid-base balance in cells, and well, that's another biological buffer, and of course, it's also an essential nutrient involved in the formation of DNA. So we've already kind of discussed this, but this is a great graphical representation of it, and I want to point it out. So we already mentioned how elements can give or take electrons, and when that happens, they don't just form these individual ions, they form a new ionic compound. So that electron always has to go somewhere. So for example, sodium gives up his electron and gives it to chlorine. That chlorine now becomes chloride. You have sodium ion now and chloride ion, and together they form the new compound sodium chloride. So that's the result. This is called an ionic bond. It's this type of bond. That bond is a strong attraction between something with an atom with a full positive charge and an atom with a full negative charge. So all of our ionic compounds are going to be solids when they're not dissolved in water or some other solvent. So it's a very strong attraction. So they're not going to be liquids. It's not going to be a very fluid attraction. That sodium isn't going to be able to pop off of that chlorine very easily. It's going to take some energy to get him away from him. And that's why they have a very strong bond and they form a solid ionic compound. We already mentioned that the number of ions that combine to form an ionic compound is determined by the charge of the cation and the charge of the anion. So we discussed calcium chloride. Calcium takes on 2+ charge, chlorine takes on a -1 charge. So you've got to flip the numbers around in their chemical formula to get the math to equal out to have a neutrally charged compound. So because calcium has a 2+ charge and chlorine only has a -1 charge, you need 2 chlorines. So we'd have CaCl2 in that case. This is a great example of that. So this is an example of aluminum oxide. This would be aluminum rust. So if aluminum reacted with oxygen and gave up its electrons to oxygen, aluminum would take on a 3+ charge. So we're talking about aluminum 3 ion. We have to be specific because it's one of those weird transition metals. I think aluminum might only have a +3 state. Oxygen is always going to take on a -2 charge because he's in group 6 of the periodic table of the elements. So one thing we can do is just flip the numbers around and put them in subtext. So we can take that 3 and put it on the oxygen, take that 2 and put it on the aluminum, and the math will work out. If we take, now we have 2 aluminums, each with a 3+ charge. So 2 times 3 gives us a 6+ charge. If we take a look at our oxygen, we've got 3 oxygens, each with a -2 charge. That gives us a -6. So overall, we have 6 minus 6, that gives us 0. So we have a neutrally charged and happy compound. So this is an easy way to balance chemical formula or check chemical formula. So in order to name the full ionic compound, all we're going to do is read off the name of the metal followed by the name of the non-metal ion. So we've got, for example, sodium chloride. It's not sodium chlorine, it's sodium chloride. So we're not going to bother to say sodium ion chloride. It just gets a little redundant. But that's, so we'll just say sodium chloride in that case. So when we're writing out, guys, for the transition metals, we're going to skip the we're going to skip the ion and copper 2 ion part. But we still have to tell you what's the charge on that copper, because copper is one of those weird guys. You can have multiple charges. I think it could be copper 1+ or copper 2+. So we have to specify that. So we're still going to say copper 2 oxide when we're talking about transition metals. So for polyatomics are pretty easy. You're just going to name the ion and then name the polyatomic ion. So this would be calcium phosphate. All calcium is always going to have a +2 charge, so we don't have to specify what kind of calcium we're talking about. All phosphate is going to have a -2 charge as well, or sorry, a -3 charge. So we don't have to specify that when we're naming ionic compounds with polyatomics. We'll just say calcium phosphate. So finally, we're on to our covalent bonds. So covalent bonds are different from ionic bonds. In an ionic bond, an electron was totally transferred from one atom to another. In a covalent bond, the electrons are going to be shared between the two atoms. So in this case, each atom is going to bring along one electron, and the electrons are going to form what we call a covalent bond, and a covalent bond is two electrons shared between two atoms. Each atom has to bring one electron in order to form a covalent bond. You can't have one guy bringing both electrons. So it's got to be a give and take sort of situation. So we'll see that that's going to be important. We're going to have to look at the number of valence electrons and how many free electrons an atom has to bring that can be used to form a covalent bond. So when covalent bonds are formed, we form something called a molecule. It's different from ionic compound. We call ionic materials compounds because if you think about it, sodium chloride is an example of an ionic compound. It's more of a crystal. It doesn't exist as individual units of one sodium and one chloride strung together. Whereas molecules like H2O, water, is a covalent molecule. So you have two hydrogens and an oxygen existing as a separate individual unit. They don't form a crystal, unless of course you freeze water and then it forms a crystal. But as water is like a liquid, those individual water molecules bounce around and can interact with one another. The individual units of sodium chloride don't do that. They're just all locked up together in a fixed crystal. There's no fixed individual molecules in ionic compounds. So here's an example of two atoms that are both not satisfied. They don't have their octet fulfilled. So what they're going to do is form a covalent bond. They're going to share that. We've got two chlorines. If these guys were to form ions, both of them would want to steal an electron. But neither of them is willing to give up an electron. So rather than allowing their electrons to be stolen, they're going to share their electrons. They're going to come together and decide to share their electrons to form a covalent bond. So if we take a look at chlorine here, it's got 7 electrons in its outer shell. 6 of those electrons are what we'll call lone pairs. Electrons kind of buddy up because electrons they can come in pairs because they have opposite magnetic fields. So one electron can be spinning in one direction, and another electron can be spinning in the opposite direction. And just like if you bring two magnets together, they can form these pairs. So we'll often see electrons come together in pairs. We'll discuss that better in class. I'll show a diagram of that on the board. But we have to know that electrons come in pairs. So you can have bonding pairs and non-bonding pairs. If we look at the valence electrons in chlorine, it's got 1, 2, 3 sets of electrons that are already paired up. And it's got this one lonely little electron that can then pair up with that other lonely electron on the other chlorine to come together to make a new bond. So in the end, what you're going to have is you're going to have 2 chlorines, and each one of them is going to have 8 electrons around him. So let's take a look at that. We've got chlorine with 1 lone pair, 2 lone pairs, 3 lone pairs, and a bonding pair. So this chlorine is surrounded by 2, 4, 6, 8 electrons. This chlorine is surrounded by 2, 4, 6, 8 electrons. So both chlorines now have met their octet rule. They're sharing these electrons involved in the bond. So even though they each came to the table with 7 electrons, now they all have 8 electrons surrounding them and their octet is satisfied. If we take a look at the outer valence shell of an atom, we can determine how many covalent bonds that atom can form. So for example, carbon has 4 electrons in its outer valence shell. In order to form or to get its octet, carbon would have to make 1, 2, 3, 4 bonds. Each one of these electrons would have to gain a pair buddy. They're going to have to bond with somebody else. Oxygen, on the other hand, already has 6 electrons in his outer shell. These electrons are going to be what we call lone pair electrons. These are going to be our bonding electrons. These electrons are not buddied up with anybody, so they can be used to form a bond. So remember, each atom that wants to form a bond has to bring a single lonely little electron along with it to be involved in that bond. Carbon can form 4 bonds, as we just said. Now, it can do that in multiple ways. It can form a single bond, so a great example would be methane gas. Hydrogen has a single electron, and so he can form a single bond. So you'd need 4 hydrogens to form bonds with carbon, to form enough bonds to make carbon happy. Another example would be a double bond. I'm going to use this carbon here as our example for our double bonds, but carbon can make a double bond. A double bond would be it has 2 bonds, or it shares 2 electrons with its neighboring atom. So a great guy that shares 2 electrons would be oxygen. So you could have oxygen here and oxygen here. Oxygen can make 2 bonds, and carbon can make 4 bonds. So here we have carbon dioxide. Now we draw these little dots here. These would represent the lone pair electrons on oxygen. These were the electrons that are not used in the bond for oxygen, so we call those a lone pair. So to continue that on, if we look at this next guy, we can even have a triple bond. So an example of an atom that can make 3 bonds is nitrogen. Nitrogen has 5 electrons in its valence shell. So you've got 1, 2, 3, 4, 5. So you've got a lone pair here. So that's not going to be involved in a bond, but you can make 1, 2, 3 bonds with nitrogen. So here carbon can bind with nitrogen, and here it could bind with hydrogen, and this would be hydrogen cyanide. This is a really deadly gas. It liberates cyanide in your body. So this is an example. We left out on nitrogen. We'd want to show these lone pair of electrons here on this nitrogen. So now let's take a look at some of these guys. Carbon here, in our first example, which was methane, has 1, 2, 3, 4 pairs of electrons. So he's got 2, 4, 6, 8 electrons around him. So his octet rule is satisfied. Hydrogen, each hydrogen only has 2 electrons around him. But remember, hydrogen has that smaller shell that can only hold 2 electrons in it at all. If it can hold any electron, if it has any electrons, it can only hold up to 2. It's a small shell. So each hydrogen is satisfied. If we took a look at our CO2, this oxygen, he's got 2 lone pairs, so that's 4 electrons, and 2 bonding pairs. So that's 4, so he's got 8, and the carbon also has 8 around him. If we take a look here at this carbon, he's got 2 from the hydrogen bond and 6 from the 3 nitrogen bonds. So he's got 8. And our nitrogen is happy as well. He's got his 2 lone pair electrons and the 6 from the bonds with carbon. So everybody's got their octet and they're all very satisfied. So here is several different ways that the elements of the different groups can form covalent bonds. Hydrogen only ever brings 1 electron to play because he's only got the 1 proton, so he's only ever going to be able to form a single bond. Carbon can form 4 bonds. He can do that by forming 4 separate bonds, as we see here. He can do that by forming 3 bonds. He's got 2 single bonds and a double bond. He can form 2 double bonds, or he can form a single bond and a triple bond. These are all going to have various shapes. So we're going to talk about how this shape here is going to form what we call a tetrahedron. If you think about it as like a 3-sided pyramid. When we look at this in 3 dimensions, when we have these 4 bonds, it will form a tetrahedron. This one forms a planar triangle, so a 2-dimensional triangle. We call that the trigonal planar shape. We'll talk about that in a little bit. These two are both linear. Nitrogen here is going to have 1 lone pair and can form up to 3 bonds. So in this case, he can form 3 bonds here, and we call that trigonal pyramidal, and we'll show some examples of that. It's kind of similar to the tetrahedron shape of carbon. We'll show why that happens as well. Here, it can have what we call a bent shape. This looks linear, but these lone pair electrons repulse each other, so they're going to kind of push these bonding electrons down a little bit. So it'll take on sort of a bent shape. So you'd have something in reality that looks more like this than what's shown up there. So this would be bent, and this would be a linear molecule here because you just have a linear bond between nitrogen, whoever this guy is here, that'd be linear. Oxygen forms this bent structure as well. It looks linear now, but if we take a look at like water, we'll often draw water like this to show you that when oxygen makes 2 bonds and has his 2 lone pairs, he's often a bent molecule. Or oxygen can form a linear molecule. So for example, O2, he can form both of his bonds with a single bonding partner to form oxygen, or O2. This would be an example of a linear molecule, and this would be bent. All of our halogens, so fluorine, chlorine, bromine, in a similar fashion to hydrogen, they can only form a single bond, and they're going to have those 3 lone pairs. So those are all going to be linear shapes as well. So now that we've seen how many bonds some of the different elements of the periodic table can form to make compounds, we're going to take a look at how chemists represent compounds on paper when we're discussing compounds. So there are a few different ways that we can do it. We can give things called the molecular formula, which is really the minimal amount of information. So the molecular formula for a covalent compound identifies all the components, meaning the atoms, in a molecule. So for example, glucose has a formula C6H12O6, and that tells us we have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. If you notice, we haven't reduced this to the smallest whole number ratio. You could reduce this to CH2O, but we're not going to do that because an individual molecule of glucose has 6 carbon atoms. So we're not going to try to numerically reduce that formula. It's different from ionic compounds. So for example, ionic compounds exist as crystalline structures with many atoms of the involved elements. So like sodium chloride, for example, a single sodium chloride crystal can be quite huge and have millions or billions of atoms of NaCl. So we wouldn't say Na 1 billion, Cl 1 billion. We bring that down to the smallest whole number ratio. So we just say NaCl with a single one of each. For covalent compounds, there's a very specific number of atoms that make up these individual little units that we call molecules. So that number or ratio in the formula tells us how many of each atom are involved in an individual molecule that can be floating around in solution or making up a chunk of solid or something along those lines. Now, the downside with formulas are very simple, but they don't tell you anything about structure. For example, there are many different sugar molecules. There's glucose, lactose, galactose, and they all have the same formula, C6H12O6, but those 6 carbons, 12 hydrogens, and 6 oxygens can be strung together in different ways. So we need to have ways to show structure. And when we write these, we need to represent things in 2 dimensions. And these are 3-dimensional molecules, so we're going to be representing them in 2 dimensions. So we're going to talk about how chemists do that and what you'll be expected to know for this class. So one of the simplest ways that we show a 3-dimensional object in 2 dimensions in chemistry is to draw what we call the Lewis structure. The Lewis structure is kind of like an electron dot representation, except we turn electron pairs into lines or into pairs of lone pair dots. So for example, if something is a bonding pair of electrons, we've mentioned before that electrons tend to come in pairs, but bonding pairs of electrons are represented by a single line between the two atoms sharing those electrons in the bond. So for example, here we have a carbon atom he brings 4 electrons to the table, and we have 4 hydrogen atoms, each bringing a single electron to the table to make 4 individual single bonds. And so the Lewis structure would be this right here on the right. That's our simplified Lewis structure for methane. Now, methane is actually a 3-dimensional object, and we'll talk about that in a little bit after we cover nomenclature. So when we talked about ionic compounds, we had some rules for naming them. We just you name the metal first, then you name the nonmetal. We might throw a prefix in front of there, depending on how many of each you have. But for covalent compounds, it can be a bit more complex. Covalent compounds is a little more difficult to predict how many of each thing you have in there. For example, if you have iron 3 chloride, you know you're always going to have 3 chlorides there. But I can have different types of carbon or different ratios of carbon and oxygen strung together. So we need to have a naming system that tells us how many of each we have for these covalent compounds, because they can be a little bit more diverse than our ionic compounds. The numbers in the ionic compounds are a little easier to predict based on the position of the elements involved in the periodic table. So for binary covalent compounds, these are things with 2 atoms that have covalent bonds. So the first thing we're going to do is we're going to name the first element in the formula. We might throw a prefix on there. The second thing is we're going to name the second element in the formula and change the ending to IDE. And third, we're going to designate the number of each element present using one of the Greek prefixes. And oftentimes we'll ignore one of the Greek prefix mono. We'll talk about that in a second. So one example is water, H2O, and you could call H2O dihydrogen monoxide. But H2O is such a common molecule that we just have a normal name for it, which is water. Ammonia is another example. We could call this nitrogen trihydride, but we often just call this ammonia. So these things can have more complex names than the ones that we're used to using. So here's an example of the Greek prefixes. So we could say mono, di, tri, tetra, penta. Typically, we won't throw the mono out in front of the first guy. So we could have a mono here because we only have one. So there should be a mono right there for our carbon. But often we just won't say the mono because it's kind of redundant. So we'll say carbon monoxide. Since we didn't say dicarbon monoxide, we're pretty certain there's only one of the carbons. We throw the mono in front of the oxygen as the second word in there. I didn't make up the system, it's just how it is. Carbon dioxide would be another example. So you've got 2 oxygens here. So we're going to use the Greek prefix di, meaning 2. So we use carbon dioxide. Here we have 2 nitrogens, so he's the first guy involved in the compound. So we're going to say dinitrogen monoxide for that guy. And that's how we name these guys. So here's an easy little table to tell you what naming method to use here. We take a look and is the compound an ionic compound? I mean, does it have a metal and a non-metal? Those will typically form ionic compounds. If the answer to that is yes, you're going to ask yourself, is the metal in group 1, 2, or 3? If they're in group 1A, 2A, or 3A, then we know what the charge of that metal is. So we're just going to use we don't need to use the Roman numeral thing. We don't have to use the Greek prefixes. So for example, calcium chloride. We don't have to say calcium dichloride. We know that calcium has a 2+ charge, so we know that there will be 2 chlorines involved there. So we don't use the Roman numerals or the Greek prefixes. If we went the other direction at that, if we had a metal that was not in group 1A, 2A, or 3A, if we had one of those transition metals, we would use the Roman numeral after the metal, so like iron 3 chloride, to tell us that we have iron 3 plus, and that would also tell us that we have 3 chloride ions along with that, because each chloride comes with a -1, so you'd need 3 of those to make up for the 3 plus charge. For covalent things, we're always going to have to use the Greek prefixes because it's not quite as easy to determine how many of each compound you have. So how many of each atom you have in the compound. So we'll have to use the Greek prefixes for our covalent formulas. So the next thing we're going to talk about is the concept of the mole. And the mole is really something that a lot of people have a difficult time with, but it's really a very simple concept. So the mole is no different from a dozen. A mole is just the chemist's dozen. So it's something that chemists use to relate quantities of molecules to one another, because each molecule of a different group is going to have a different weight. So for example, glucose is going to have a different molecular weight than water. So if we need one water molecule for every one glucose in a chemical formula, we can't just take 1 gram of water and 1 gram of glucose, because those things weigh different amounts. You have different sized molecules involved. And because chemicals are so small, or molecules are so small, we can't use something like a dozen. A dozen is just a really small number. You'd still have an infinitely small, impossible to measure amount of material. So a mole is the chemist's dozen, and we use this huge number called Avogadro's number. Let's talk just a little bit more about what a mole is. A mole is defined as 12 grams of carbon-12 contains an amount of atoms equal to a mole. That is the definition of a mole. It's the number of atoms in 12 grams of carbon-12. And it was really easy to get pure carbon. You can get pure carbon in the form of diamond, and that's why they used that. And they used 12 grams of carbon-12. They picked that because carbon, if you look at carbon on the periodic table of the elements, carbon has a molecular weight of 12. So really, the molecular weight unit equals is the weight of the simplest atom, hydrogen, actually. It'd be 1 gram of hydrogen 1 as well. So, but hydrogen's a lot harder to grab and measure. Carbon is a big solid thing, so that's why they use carbon. There's 12 grams of carbon-12, and that's the number of atoms that make up a mole. So the number of atoms present in 12 grams of carbon-12 happens to be this huge number, the 602 with a whole bunch of zeros after it. So it's 6.02 times 10 to the 23rd. So, well, 1 dozen equals 12 of something. 1 mole is 6.02 times 10 to the 23rd of something. Just like you can have a dozen of anything, you can have a dozen cars, you can have a dozen eggs, you can have a dozen people, you can have moles of anything. I could have a mole of cars that take up a huge amount of space on our planet. But you can have a mole of anything. It's just a nice large number that we can use to measure quantities of things that are extremely small. So this is a really useful number because it allows us to work with ratios of materials that don't have the same weight. So just like a dozen eggs and a dozen bowling balls have different masses, a mole of silver atoms is going to have a different weight from a mole of carbon atoms. In particular, if we say we have 1 mole of carbon atoms, that has a mass of 12.01 grams. So sometimes we'll take that number that's on the bottom of the little symbol on the periodic table at 12.01, and we'll call it the molecular weight in grams per mole. So if we ask what's the molecular weight of carbon, is 12.01 grams per mole. What's the molecular weight of a silver atom? It's 1.0 or 107.9 grams per mole. So Avogadro's number is really just another conversion factor now. Just like a dozen is a conversion factor, you can say how many units are in a dozen. You can say there are 12 units per dozen. Now we can ask how many units are in a mole. If it's atoms that we're talking about, there are 6.02 times 10 to the 23rd atoms per mole. And so it's just another conversion factor that we've all learned how to use conversion factors in chapter 1, but we'll still do some examples at the board and in some of our practice homework problems on how to use the mole and conversion factors as well. So now that we understand the concept of a mole, we can work with what chemists use or call the formula weight of a compound. So if we know the ratio in which things combine, then we can figure out the masses of the individual materials that we need to use to get them to combine to make that material. So for example, we can use CO2. So CO2 is carbon with 2 oxygen atoms. So I could tell you if I had a whole bunch of CO2, I could tell you how many grams of carbon I would need with how many grams of oxygen to make how many grams of CO2. So for 1 mole of CO2, I would have 12 grams of carbon because the molecular weight of carbon is 12 grams per mole. So the molecular weight, molar mass, same difference. So carbon is 12 grams per mole. Oxygen, if you look at the periodic table of elements, is 16 grams per mole, but I have 2 of them. So that gives me 32. So I would have 32 grams per mole of oxygen if I had 1 mole of CO2. And the mass of the entire thing, if I had 1 mole of CO2, would be 44 grams per mole. So the 44 grams per mole is the 12 grams from carbon and the 32 grams from oxygen gives you the 44 grams per mole. So that's how we calculate the molar mass. So we'll do plenty of molar mass examples and calculating those in class, but I want to move on to our three-dimensional shape now. This is where things get fun. Because all of our molecules are actually exist in a three-dimensional space just like we do. We have to represent them in 2 dimensions. And it can be kind of difficult then to determine how they're going to behave when interacting with one another if we're trying to show them in 2 dimensions. It just is difficult to wrap our head around that sometimes. So chemists came up with these kind of genius little ways to draw 2-dimensional or 3-dimensional things in 2 dimensions. So this is an example of methane. Methane has a shape that we call tetrahedral. It's a little four-sided, like a little four-sided dice. If you're nerdy enough to play Dungeons and Dragons like I was, but it's like a 3-sided pyramid. And so this tetrahedral shape has a bond angle of 109.5 degrees, and we can represent it with a ball and stick thing with shadows and everything along those lines with computers nowadays. And it's pretty easy to represent things with a computer, and we all recognize this as a 3-dimensional shape. But how do you draw that with a pencil? And this is how the chemists decided to do this. So we have different types of bonds that we can show here. These are all the same bond, so we're showing those single bonds between carbon and hydrogen, but we're going to draw them a little bit differently, and they mean different things. So if you have the normal straight line here, that means that that bond is in the plane of the paper. So that bond is just those flat against the paper. So this whole portion of the molecule exists just as you're looking at it. It's just flat against the paper. If we have the wedge, that means that this guy is sticking out at you. So this hydrogen is sticking out of the plane at you because it has this little wedge here. If we have the dash bond, that means that guy is going away from you into the plane of the paper, into your computer screen. So these are ways that we can show bonded pairs of electrons in 3-dimensional shapes. Now, one thing I should mention too is that bonded pairs of electrons repulse each other, right? So they're going to try to stay as far away from each other as they possibly can. And that's what gives rise to the 3-dimensional shapes that molecules have, is that the pairs of electrons, we mentioned that the pairs individual electrons can pair up to form these bonding pairs because they can have opposite magnetic poles. And that's why they'll be able to pair up in pairs and not repulse each other in the pair. But the bonding pairs repulse other bonding pairs because of their added negative charges. So the 3-dimensional model is called the valence shell electron pair repulsion model. It's called the valence shell model because we're only talking about electrons that are bonding electrons. All of the bonding and non-bonding electrons that we're talking about are in the valence shell. So we're talking about bonding electrons and lone pair electrons All of these things are in that outermost shell of the nucleus that we talked about. And then we say electron pair repulsion model because the pairs are repulsing each other, and that's what gives rise to these different three-dimensional. Molecular shape is kind of a hard thing to wrap your head around until you get out some molecular models and play with them. And I'm going to bring some molecular models into class and we'll discuss these. But this is kind of the easiest way that I know to describe it on paper. So the best way to look at it is to look at the number of regions of electron density around a central atom. So we're going to take a look at the central atom. So for example, our first example is methane gas. Our central atom is carbon. So carbon has 4 regions of electron density around him. So each one of those bonds is a region of electron density. Those electrons tend to be in that area between the carbon and the hydrogen. So if you have 4 bonding regions of electron density, where the electrons are involved in a bond, you're going to have the tetrahedral shape. All of your bond angles are going to be 109.5 degrees, so those bonding electrons can stay as far away from each other as possible. But still stay close to the nucleus of the atoms involved in the bonds. So the next shape that we have is if you have 3 bonding regions and a lone pair region. So nitrogen makes 3 bonds and has a lone pair. So if nitrogen didn't have that lone pair, this molecule would look like that trigonal planar down at the bottom, where it's just a flat triangle around that central atom. But if you throw that lone pair of electrons in there now, that lone pair of electrons pushes down on those other bonding pairs of electrons. So what you end up with is this pyramidal shape, like a pyramid with nitrogen on the top that you see there on the right. So we get that pyramidal shape if you have 3 bonding regions and 1 lone pair region. The next one that we get is this bent shape. So you're going to have a bent looking molecule. If we didn't have those lone pairs, this bent molecule, H2O, would look like CO2 down at the bottom, where the bonding electrons in the bonds between oxygen and hydrogen would try to get as far away from one another as possible, and you'd have a 180-degree angle. But since we have these lone pair electrons around oxygen, which is why it's really important to know how many lone pair electrons a molecule brings to the table too, those lone pair electrons are going to repulse each other and those bonding electrons between the oxygens and the hydrogens and force them down. So for bent molecules, you're going to have 2 bonding pairs and 1 to 2 lone pair regions around the central atom. And then our trigonal planar, we have 3 bonding regions. So a double bond, I want to point out, exists in a single region of space. So although we have 4 electrons in that double bond between the carbon and the oxygen, that's the same region of space. So when I say region of electron density, I'm just talking about like the bonding area. So the region of electron density in this particular model, this would have 3 regions of electron density. 1 right there, 1 right there, and 1 right there. So it has 3 bonding regions of electron density around this guy. So that would be the trigonal planar shape. And you get linear if you have 1 to 2 bonding regions of electron density. You just get a linear shape for your molecule. One of the reasons that we're carbon-based life forms is that carbon can make all sorts of crazy cool shapes depending on how many guys he's bonded to. And carbon has this awesome ability to make up to 4 bonds. So he's a guy that can make, the largest number of bonds out of those atoms in the first couple of rows of the periodic table of the elements. So carbon can make up to 4 bonds, so he can have the tetrahedral, the trigonal planar, and a linear shape as well. Now remember, this is a model, so it's not completely a perfect description of what happens in reality. But for the most part, let's talk about what's going on and how the electrons are occupying this space. We talked about how the electrons float around the nucleus of the atoms. Once they become involved in a bond, they're going to kind of occupy certain regions of space more often than they occupy other regions of space. So our non-bonded pairs of electrons, those are our lone pair electrons, they take up space, but they're kind of invisible to the molecule shape. So they influence shape by forcing the bonding pairs close together. The bonded electrons are confined between the 2 atoms involved in the bond. We've already discussed all of this, just reviewing. and the non-bonded electrons are they're not so restricted in this way, and so they take up a little bit more space than the bonded electrons. So those lone pairs take up a little more space than our bonding electrons do. So these are just some graphical representations to kind of drive home some of these ideas of how these lone pairs force these bonding electrons down into different shapes. So you've got this lone pair of electrons on the top of nitrogen here, and that forces these bonding electrons down, and it makes the bond angle a little tighter than what we saw in the tetrahedral formation, which was a 109.5. That's because that we see a 107 here, and that's because that lone pair takes up a little more space than the bonding electrons, as we discussed on the previous slide. And the same thing here with water. You've got two lone pairs, each of them taking up more space, so you're really going to force that bond angle down even a little harder to a 104.5. And you don't have to memorize these numbers, but just understand that in general, the lone pair electrons take up a little bit more space than our bonding electrons do. So they're really a force to be reckoned with as far as forcing molecules into a particular shape. So far we've been working with really tiny molecules, and I want to point out that we're going to start to work with huge biological molecules and discussing how molecular shape of like sugar atoms and proteins and things along those lines can become really complex. So I want to show you just a simple idea of how do we break this down in a larger molecule. And here's a really simple example. This is ethyl alcohol or ethanol. This is the form of alcohol that's involved in getting you drunk. But so we can see that there are multiple central atoms that we could look at. So when we talk about molecular shape, we really got to pick an atom if we're going to talk about this VSEPR theory. So if we take a look at this carbon here, he's got 1, 2, 3, 4 regions of electron density around him, and they're all bonding. And so this would be tetrahedral. And the same with this carbon. He's got those 4 bonds around him, so that's tetrahedral. This guy, this oxygen, has 4 regions of electron density around him. He has a lone pair, another lone pair, so 2 lone pairs, and 2 bonding. And so you've got the bent shape there. We've got 2 lone pair regions and 2 bonding. So you've got the bent. So this is how we look at larger molecules. You break it down by looking at the individual atoms of interest and looking at the shape around those atoms. And then you have an idea about the shape. You can start to model the shape of the entire atom after that. The entire molecule, not the entire atom after that. So the final thing in our chapter, we're going to discuss electronegativity. Electronegativity is related to molecular shape. It kind of is leading on to what we're going to discuss in our next chapter, which is how molecules interact with one another. So we talked a lot about bonds in this chapter and the formation of bonds. We talked about ionic bonds in which electrons are completely taken away from one atom and given to another atom. And we talked about covalent bonds. And in covalent bonds, electrons are shared between the 2 atoms. So we looked at methane as an example where carbon and hydrogen each bring an electron and they share those electrons in a bond. Electronegativity discusses the fact that not all partnerships allow for equal sharing. So sometimes an atom is going to be better at hogging the electrons than another atom. And that's the term electronegativity. So electronegativity is the ability of an atom to attract the bonding electrons of a covalent bond to itself. Typically, things that are on the right side, the upper right side of the periodic table of the elements, are going to have the strongest electronegativity with an exception. That's if you ignore the noble gases, because of course they don't make bonds. So we ignore the final column on the right on the periodic table of the elements when we're talking about electronegativity. So the element with the greatest electronegativity on the periodic table is fluorine. And that's because fluorine has a fairly large number of protons in its nucleus, and the protons are not shielded by many layers of electrons. So as we go from top to bottom on the periodic table of the elements, we add additional layers of electrons around the nucleus. An atom's ability to draw electrons in its direction comes from the positive charge of the protons in the nucleus. So if there's a whole bunch of these shells of electrons surrounding that nucleus, it's not going to be able to pull electrons in its direction. So our electronegativity gets stronger as you go from the bottom to the top of the periodic table of the elements, because the electrons outside of that atom are going to be able to get closer to the nucleus that way, because there's not these many shells of negatively charged electrons around that nucleus that they're trying to get to. So, and then also, as you go from left to right on the periodic table of the elements, you get more protons in your nucleus. So that's why fluorine he's got the highest number of protons to shell, the ratio of protons to lack of shells in his surrounding his nucleus. So fluorine's the best guy. He wins the electronegativity challenge. So as you go from left to right, you become more electronegative. As you go from bottom to top, you become more electronegative. So that means you're going to be able to pull electrons your way. So this is an example of an electronegativity table, and you don't have to memorize any of these numbers. I would give you this table if you needed to use it on a test. But in general, we are seeing that as you go from bottom to top, your electronegativity increases. As you go from left to right on the periodic table of the elements, your electronegativity increases as well. So when a covalent bond happens between an atom which is not very electronegative and an atom that is very electronegative, we get what's called a polar bond, where the electrons are being hogged by one member of the molecule involved in the bond. So when they are shared equally, we call that a nonpolar covalent bond. So we have polar covalent bonds and nonpolar covalent bonds. And this is what gives rise to the differences between oil and water. So water is a very polar molecule, and it's going to want to interact with other very polar things, and we'll find out why in just a second. Whereas oils, things made up of hydrocarbons, carbon and hydrogen have very similar electronegativities, so those are going to be nonpolar things. So they're going to interact with other nonpolar materials very well. So here's an example of even sharing of electrons or equal sharing of electrons and unequal sharing of electrons. So for example, hydrogen, if you have two hydrogen atoms, obviously they both just bring one proton to the table, so they're going to have an equal ability to pull the electrons in their direction. So this is a perfect example of a nonpolar molecule. Whereas HCl, or hydrogen chloride, those electrons are definitely going to be hogged by that chlorine. He's further to the right on the periodic table of the elements, has a much larger nucleus than hydrogen does, so he's going to be able to pull those electrons in his direction. So what ends up happening is you have a partial negative charge. It's not like an ion. For example, if we had sodium chloride, where your sodium takes on a full-blown positive charge, and your chlorine takes on a full-blown negative charge because the chlorine totally stole the electron. Here, the electrons are still being shared, but they're more often going to be floating around the chlorine than they're floating around the hydrogen. So the chlorine is hogging it. So we use this Greek delta symbol to represent that this is a partial charge. So you can have a partial positive charge on the hydrogen and a partial negative charge on the chlorine. We'll also use this funny looking arrow with a cross here. So this arrow shows us the direction in which the electrons are moving. And that helps us show where the pole is. So you've got the polarity. This shows the polarity. It shows that the negative side of this molecule is over here, and the little plus side of this arrow shows the positive side is over here. So you've got a partial positive and partial minus. So you can either use these deltas, or you can use this arrow with the cross in it to show your polarity in your molecule. So just to recap, if you've got a covalent bond and those electrons are not shared equally, then you're going to have a partial negative pole and a partial positive pole. So we call these bonds polar bonds. A bond that is nonpolar is going to have no ends or no poles. And these molecules are not going to stick together like magnets, whereas your polar molecules, as you can see, they've got a partial negative and a partial positive. And we know that opposite charges attract one another. So our polar molecules are going to be attracted to one another and kind of act like little tiny molecular magnets. So if you were to take a drop of gasoline, which is a very nonpolar material, and put a drop of that on a table, and then take a drop of water and put that on a table, the gasoline is going to go flat on the table and then evaporate. there are very little forces holding that together because these nonpolar molecules, they don't have poles. They don't act like magnets. Whereas what happens to that drop of water? It forms a bead. It actually fights gravity. And that's because you have tiny little molecular magnets with positive and negative ends in it. So that's why water is so freaking amazing. That's why it can exist in all three states across our globe. So it can exist in the frozen state, the solid state, the liquid state, and the gaseous state. It acts like these cool little magnets that hold each other together. So the stronger that electronegativity, the more polar the bond, and the stronger the interaction between molecules is going to be. So electronegativity is going to be a huge player in how strongly molecules interact with one another in chemistry and biological chemistry. So how big of an electronegativity difference do you need to go from polar to nonpolar, or from nonpolar to polar? If you're in the range between 0 and 0.4, that's the difference between electronegativity of the atoms involved in the bond, then you have a nonpolar covalent bond. If you're in the range of 0.4 to 1.8, you have a polar covalent bond. Anything above 1.8 is ionic, and the electron has been fully transferred to the other atom. And as we start to draw molecules on the board in class, we're going to talk about what types of bonds are polar versus nonpolar. And the really important ones in biology and biological chemistry are the carbon to hydrogen bond is going to be nonpolar. That's the most common nonpolar one that you have to remember. Oxygen to hydrogen, those bonds are going to be polar. Nitrogen to hydrogen, that bond is going to be polar. And oxygen to carbon, that bond is going to be polar. So the further apart from the two nonmetals are on the periodic table, the greater the polarity of the bond between them. So for example, oxygen and carbon are closer to one another than oxygen and hydrogen. So the polar bond between oxygen and hydrogen is going to be a lot more polar than the bond between oxygen and carbon. Now, carbon and hydrogen, they are in different rows, so there's kind of like a diagonal thing happening there, which is why their electronegativities are so similar to one another. But in general, we just have to remember then that carbon to hydrogen bond is very similar. Their electronegativities are almost equal to one another. So far when we've discussed polarity, we've just talked about a single bond between two different atoms. So if you've got one atom that's very electronegative and another atom that's not very electronegative, then you can have a polar bond. But how do we scale this up on the molecular level? Like if you've got more than one bond in a molecule, how do you determine whether something's polar or nonpolar? So we're going to discuss that now. So you would imagine that if something has polar bonds, that you're going to have a polar molecule. That's not always true. And we'll see that sometimes you can have multiple polar bonds that cancel each other out if they're pulling in perfectly opposite directions. So they can equalize each other so you don't end up with a polar molecule. So again, imagine like our planet Earth as this sphere, and you've got a clear positive side and a clear negative side on our north and south pole. But if you had many different directions that the magnetism was moving in, you could neutralize that charge overall. So that's something that can happen here. And we'll show an example of that in a second. So in general, a polar molecule has an uneven distribution of electrons over the entire molecule. So we'll see an example of that like water here in a second. And a nonpolar molecule has a pretty even distribution of electrons around the entire molecule. For molecules that contain only two atoms connected by a covalent bond, the polarity of the molecule is the polarity of the bonds. It's really easy to figure out whether a diatomic molecule is polar or nonpolar. But when you have three or more atoms, you have to consider the electronegativity of the atoms and the shape of the molecules. So that's why it's important to understand the VSEPR shape, those different shapes, before we start talking about polarity for molecules. So here's a great example of two molecules that look like they should both be polar molecules. But one is polar and one is nonpolar. And that's because they have two different shapes. So if we take a look here, carbon is not very electronegative compared to oxygen. So you've got two different polar bonds here. So you've got electrons going in this direction, and you've got electrons going in this direction. So where's the polarity here? How is there one side of this molecule that has more electrons than the other side of this molecule? And we'll see in a second, no, there isn't. Whereas this guy, it looks like you have the same situation. You've got, instead, whoops, you've got electrons going the other direction. I screwed that up, let me fix that. So you've got electrons going to the center. Electrons going to the center. But what's really important is we have to think about this in 3 dimensions. This is a linear molecule. So you've got negative, negative, and positive in the middle. This is not polar. If we look at the Earth, you've got, it acts like a magnet. You've got a plus side and a minus side. So we don't have that situation going on in carbon dioxide here at all. If we look at water though, the electrons are going in this direction. So you're going to have, if we circle this guy, you're going to have a negative side and a positive side down here. So you do have a polar molecule with water. So that's one of the reasons that water is a polar molecule. It's got a positive and minus side. So the individual molecules are going to act like little magnets and be attracted to each other. So that's why water is a liquid at room temperature. Whereas carbon dioxide, which actually weighs more than water, so you would think that it would be a liquid too. It would be heavy and be a liquid, but it's not polar. There's nothing holding individual or molecules of carbon dioxide together, so it exists as a gas. So this molecular polarity and molecular shape, understanding this allows us to predict how a particular chemical is going to behave. Even these small molecules, and we can scale that up to these large molecules and start to predict like how drugs are going to bind to a pocket in a protein to prevent a disease state, to either inhibit that protein or enhance its function. So that's how these electronegativity and molecular shape is going to translate into medicine. As we start to understand these interactions between molecules, we can start to make predictions and design drugs and new medicines.